Alright, so I thought I'd go through a few examples here, or at least one example, of using our code to do some training. And before we do that, I just wanted to explain some of these files that you see here. I don't think I'll probably, I might include the EDM file. The EDM file is short for Euclidean distance matrix, and so it's a little function that will find the number of, well, if you give it two sets of matrices, well, two matrices, one that's a number of points by dimension, and the other is the number of its points by dimension, and the dimensions match. Then the return is a distance matrix that is going to be number of points in W by number of points in P, right? So that's just giving you back all the distances. Okay. I've actually got that built into the RBF code here, so you don't have to call that separately. For the RBF code, I've got one that's RBF OLS, and OLS stands for orthogonal least squares. And so you'll see here in the orthogonal least squares code that we're going to be building a neural net or an RBF network, but we're going to be using orthogonal least squares to do it. And so we're going to have a goal and a maximum number of neurons. And we'll also pass it x and t, so those are our training data sets. And just to be explicit here, x and t should be dimension by number of points. And I do a little error check at the beginning to make sure everything's working correctly. Because actually the piece of code is pretty easy. All it does is call the orthogonal least squares routine, and that builds everything, all of our training parameters that we need. Okay, and so once this is done, you get a data structure back called net params, and you can see here what net params is storing. So we're in matrix C, it's the centers, and those are the actual centers, so that's going to be dimension by number of centers. We'll also be looking at the weights and the bias and the spread. The spread is for the Gaussian function. Actually, it's going to be the reciprocal of the spread, so you're going to be multiplying SPR times your distance. We'll see it in just a second. And then the TR is our training error. So if you want to check to see what the training error looked like, you can do that. And so where this is actually computed, you can see it. Where is it? Here, B is kind of the actual spread that you're going to have. And there's a little blurb in one of the exercises that talks about where this came from. But you can see here that the spread is actually being multiplied by distance, the distance matrix. And so, yeah, so it's not divided by like we would assume. Okay, and then, yeah, and then the radial basis function here is the Gaussian. And so all that does is computes e to the minus whatever this is squared. Okay, so that's really all we need to kind of know. Just know that what comes out of training is net params, and that data structure contains all of the information that you need in order to work with the RBF. Okay, and then what you'll do if you want to predict on the RBF with new data is you would just put it in RBF predict, and so the syntax is just y equals RBF predict, and then the net parameters, comma, whatever data points you want to evaluate your RBF at. And you can see exactly what's going on right here. How we're using all of our parameters is just laid out right there. Good. So these are both pretty well self-contained now, and so I'm going to try them out on Octave for the first time, and I thought I would bring you along to see if everything is going to work. Okay, so I think I'm in the right file here. I'll clear everything out, and I think I've got some stuff ready to go here in the Wine app. What's going on in the Wine app? So here we load the wine classification. In fact, yeah, we can go ahead and run a few of these. Let's go ahead and just run the first few. Oh, let's just go ahead and run this. Here you can see we're going to load the data first. And what that does is it loads matrices X and T. And then I have to change the classes because my targets in here are 1s, 2s, and 3s. And I would rather have 1, 0, 0, 0, 1, 0, and 0, 0, 1. We talked about that before as my targets for the columns of the identity. Okay, so that's what this is doing. This is kind of a neat little trick. You'll see here that this is the target value. Those are the indices. So what's happening is I'm copying the columns of the identity into this matrix T. Right, so for example, this T prime might be 1, 1, 2, 2, 3, 3. And so this is taking copies of the identity, column 1, column 1, column 2, column 2, column 3, column 3, yeah, and so on. So that's kind of a neat little trick there. And so capital T now is 3 by the number of points. And then we'll split our data and see what happens. Good. Okay. YNAP 0. Let's see if this works. By the way, I highly recommend writing your code in an app like this. Well, we got some output. What's happening here? It looks like I don't think the predicted classes are all class 2, or it looks like, sorry, I didn't mean that. It looks like the predicted classes are all class 2 for some reason. I wonder what happened. Let's take a look. We can take a look at our net params. That spit everything out instead of in MATLAB it usually doesn't just spit everything out at you like this. Let's see. So spread. So here's our training error. Let's take a look at our training error. Oops, that was net params. Well, that looks good. Our training error was decreasing as we increased the number of nodes. What else? Let's call, oh, maybe we can see here. I wanted to see what some of these were here. There you go. Net params.c. Okay, so this is just the centers. I don't need to see the centers there. What did the matrix W look like though? There's matrix W. That's kind of interesting. And our B. Let's see. And so let's see how many centers did we get here. So let me say temp equals net params.c. And then how big is temp? 62 by 13. So that's a lot of centers. But it didn't max it out because over here we see the number of centers is 70. Well, this is kind of odd. I say you should not do this, but we were checking to see if our code is correct. So let's go ahead and uncomment the stuff that we're not supposed to do. And I'll comment out the stuff that we did. And let's see what's going to happen. So what we're doing is we're predicting on our training data. You know, we got such a crappy result that I would like to see that were we actually predicting on something? Is our code correct? So that's why I say you shouldn't measure the error on your training set, but we want to make sure that our code is correct because this sure looks really weird. So let's clear and let's try calling YNAP 0 again. Ooh, boy, look at that. So what's happening is we're getting really good results. I mean, perfect results on classes 2 and 3 on our training set. But what happens when we put in our test set? We got really terrible results. What is going on? So let's just verify that one more time. So I'm going to go ahead and re-comment these out. just to be clear, what you're looking at here is the confusion matrix on the training data. Okay, and so now we're going to go back to the testing data to see what happens there. And so if we go back to our training data again, our testing, let's go ahead and clear out the old stuff here first. Try running that one more time. Oh, oh no, what's going on? Can anybody help? So we're getting really good results with the training set and terrible results on the test. You know what this means is that we're basically memorizing the data. We're memorizing the data, and so we're not getting any generalization at all. Why is that? What's going on? I have a suspicion, and this is my suspicion. My suspicion is that I have a feeling that one of the variables in the wine classification is saturating all the others out. And so instead of using 13 input variables, we're basically just using one. Now, I'm thinking that because otherwise the generalization should be very good here. We shouldn't get results like this. Okay, so what's the fix? Well, the fix is to scale the data. So let's go back into this. I need to scale my data, and so I've got a scaler right here. Do you remember we made that up? And so let's go ahead and scale our data. And so in the wine app, once I load in my wine classification, let's go ahead and say x scale, or xs, and then the scaling parameters are going to go into params is equal to standard scalar, and then our x, and then n is the dimension. I do that because yeah, I want to double check. That's kind of a reality check for the program. So we have 13-dimensional a 13-dimensional data set there. We don't have to worry about the output, right? Because we're creating the output right here. It's just the input that's a problem. And then when we do the scaling, we'll go ahead and split the scale data. So we're keeping our original data clean for now. Excuse me. And now let's see what we do here. Think it's going to work better? I hope so. In fact, what we could do maybe is just let's just run these two lines and see if it's true what we suspect. What does that mean? Oh, that was supposed to be an equal sign. Did I put a minus sign there? I did. Okay. And now what I want to look at is the scaling parameters. What are the scaling parameters that are being used? Okay. The mean is running from 13 to 19. Uh-oh. There you go, right there. The last column has a mean of 746 and a standard deviation of 314. So what's actually been happening in our code probably is that the 13th variable is just saturating all the other variables. The other variables, it doesn't matter what they are, because this last variable is so large, we're just going to be focusing on that particular variable. Okay, and let's see if that's right. Do you think I'm right? Let's give it a try. Oops. What happened now? Call from train test split. Let's take a look. I'm going to pause for a second because I think I just want to verify that this is the correct version of this piece of code. Okay, that was my error because I I wanted the data to be dimension by number of points for these, and you'll notice that x sub s right now is number of points by dimension, and so I just went ahead and transposed that now. So I think it'll work. Now let's try it again. Oh wow, whoa, what happened there? Is that the classification on the training set? No, it's not. That is classification on the test set. Yay! Very good. So we've discovered something about our scaling, right? Um, yeah, what's happening is class 3 is still having trouble being classified. There's more being classified as class 2 than class 3, but I think these two classes were kind of blurred, or two of the classes were kind of blurred together a little bit. Anyway, I think we saw that in the PCA before. Looks like class 1 is pretty well separated from class 2 though. Very good. And so I would say that this is a pretty successful clustering for right now. Did we do a better job in the linear neural net? I don't remember. I will say, when you're using these Gaussians for your transfer function, yeah, I find that a lot of times you need more basis vectors or more centers than you would otherwise. Yeah, so in fact, maybe we can take a look at the RBFOLS for a second. And oh no, I don't want to do that. I was just thinking, you know what, I might change my transfer function to be a cubic instead of a Gaussian, but I've hard-coded the orthogonal least squares algorithm to work with just the Gaussians. So this RBFOLS is actually MATLAB's new RB. This is MATLAB's code, or old code, I should say, for solving the radial basis function centers problem. Okay, and so I'll have you work out an example with the OLS algorithm. So just like we did here, I'll leave you the wine app 0.m as example M file. What we're going to try to do next is try to use a clustering algorithm to find the number of centers, and then we're going to be able to use RBF1.m in order to change the transfer function to be like a cubic or a multi-quadric or yeah, all those other things. Cauchy is kind of a fun one to try. Good. All right, so I'll stop this one here, and I'll be sure and put this code on our class website.